Okay, are there any questions from last time? No questions.
Sir?
You said that so we neglected the vacuum, saying that the only energy relative to the vacuum movement.
Right. Well, that's not the only yeah, but we also said one more thing, which is that when we go from the classical theory to the quantum theory, there's some intrinsic ambiguity in that. But I said two things. But go on with your question. Yeah, yeah. About what? Casimir effect. Huh. Good. Go on. Yeah, yeah.
It seems that like the vacuum energy does.
Well, the point is you have to be a little careful of what you're asking. What you can try and ask is, let's say I set the energy of the vacuum to be 0. Okay? And then I ask for a different operator, which is the integral of, we'll discuss the stress tensor today actually. So we are going to have one more lecture, by the way, but so you can discuss a different operator. So let's say once you've defined the vacuum everywhere to have 0 energy, right? You can then ask for this operator, which is from 0 to, not from infinity, but from minus some L to L, okay? Where this is the density. This is the Hamiltonian density, understand? You can ask for this kind of an operator. This kind of an operator will not annihilate the vacuum. You can check that. Okay. So if you, let's call this, what should we call it? Let's call it H hat. Okay. So the vacuum is defined as H of 0 is equal to 0. But that doesn't mean that H hat of 0 is equal to 0. In fact, you will find it's not equal to 0. Okay. It's equal to some other state. And the Casimir energy is basically a measure of this. Now you could say, why can't I choose H hat of the vacuum to be something? So the first issue is that this operator has some non-trivial dependence on this L. What you're really measuring is, let's say I decide that the integral out to infinity is 0, then what is the integral up to a finite region? Alternately, let's say I decide that this integral is 0. What happens if I change L to L plus delta L? Okay. And that's something that's meaningful. Okay, so let's say I look at a state where this is 0, whatever, right? You can ask what happens if you change the length a little bit. So what is always meaningful is how this energy changes as a function of length, not its absolute value. Okay? And when you measure this Casimir energy, usually what is done is you say that the integral out to infinity is 0. If that is 0, then the integral from minus L to L is not 0. Yeah. Okay, good. Are there any other questions? There was some question online, right? No? Someone said something online.
Sir?
Yeah, yeah. You can hear.
Sir, last time. Am I audible, sir?
Yeah, go on, yeah.
So last time you introduced the Schrodinger functional representation,
Yes.
right?
Yes.
So when we represent psi as phi as a function of phi, where phi is the scalar field, so can we do the same can we represent it with the momentum pi as a functional?
Yes, you can think of it as a function of the momentum pi as well. That's right. That would involve doing a functional Fourier transform. So if you have like
Right.
Yeah. So let's say you have psi of phi, and you can do something like this. And then you'll have to do an integral over. This is a functional integral. You have to integrate over all phi's. Yeah. If you do this, you'll get functional of phi instead. Exactly the way you do for position space. Let's think of it differently. Let's think of, whenever you get confused by this, think of a lattice generalization, right? So you have phi 1, phi 2, phi 3, phi 4. And let's say I have a function of these psi i's, right? And then to go to momentum space, all I need to do is do this, right? I sum of phi I. Can you see this?
Yes.
Okay, so this is now, let's say I had 4 or 10 or whatever fields, right? And this is the continuous version of that, which is a functional integral. And this sum has become an integral. But it's the same formula effectively. this one, the one above the line, and the one below the line are effectively the same formula.
So my question is, like we have a commutation relation for phi and pi.
Yes.
So is there any commutation relation for these two also? Functional representation of the fields?
What do you mean commutation relation? Psi and pi always have the same commutation relation, right? We always have phi pi. This is always true. I'm not writing t equal to 0, but this is always true, right?
Right. So suppose if we write like for psi of phi and some chi of some other functional, instead of phi we write phi prime, right? You have written x and x prime, so I'm saying phi and phi prime.
Phi and phi prime. You mean this and sorry, I'm not. Just, you know, if you're getting confused, think about the wave function. Can you tell me in non-relativistic quantum mechanics what would you be looking for? Let's say you have your wave function psi. You can write it as psi of x, or you can write psi of p. Yeah. So what do you want there?
We want to have the relation to the operators x and p.
The operators are there. Those are the operators. But see, the operators here act in the same way. I'm not. Let's say I differentiate the operator, right? Then on the wave function of phi, it just acts like phi. Right? In the phi, the same as what you have in non-relativistic quantum mechanics. If you think of the operator, how does it act on psi of x? It's like x psi.
Yes, same, yeah.
Okay, and pi acts like a derivative on this. If you think of this pi representation, then the operator phi will act like a derivative, and the operator pi will act like multiplication.
So the same. When we write the relation, which is the same as those of in the non-relativistic quantum mechanics.
I mean, what the relations are the same, meaning this is conceptually the same thing. It's just a wave function. It's not something different. You know, it's a wave function. It's a wave function of some variables. You can think of it as a function of those variables, or you can think of the wave function as a function of conjugate variables. And it's the same thing.
Okay. So then my actual question was like, if we have a functional of phi, psi of phi, that's a functional, and we have another functional chi of phi prime, right?
Okay.
Chi of phi prime, where chi is the momentum of that psi, corresponding psi.
Okay.
So we will have a commutation relation of those two.
What does that mean? In quantum mechanics of a single particle, would you have, if you take psi of x, the wave function, and some other like chi of p or whatever, chi of some other particle, what commutation relation? The functions, right?
Oh yes, right. Yes. I understood you.
Okay. Okay. Thanks. Yeah. Okay. Great. So far we've discussed the field in space time. Yeah. Sorry, we've discussed the field in space, and you know, we soon want to do something more Lorentz invariant. Thanks. Okay. Okay. Yeah, I came a little early. Yeah. Oh, sorry. Before I go further, since I remember this class in question thing, we'll try and have another class. Maybe it won't. We'll do like 1 hour 20 minutes or something, so you can get away for the 5:30 shuttle, and that's okay, right? 5:30 is a shuttle you guys take mostly. 5:45. Okay, fine. So then we can finish by. So we'll. That's at 4 o'clock, and this room is booked, right? So this is because next Monday we'll have a class, but after that, on Wednesday after that, and on Monday and Wednesday after that, we don't have. So we'll miss some classes then. That's why I'm doing a double class now, and we'll do a double class later, and maybe I'll see if I can get someone to give a guest lecture next Wednesday or the week after. Yeah, but because we're going to miss a few classes, I'm doing some extra lectures now. Okay, good. So far we've discussed the field at t equal to 0, yeah, which is, and we've written down some formulas for it. And however, it's okay to pick some coordinate system and to work within that coordinate system. But in the end, we want to work within a space time. Right? In particular, this coordinate system that we've picked is a little arbitrary. Right? We picked some particular Lorentz frame, and we said, in that frame at t equal to 0, we have some value of x. Okay? But in fact, the position x is not, a well-defined quantity. Okay? So if you want to compare, not to say anything about current events, but if you want to compare x at t equal to minus 5,000 years and x today, then this is not something well defined. Okay, if you want to say that x at some point was something, and we're at the same position as we were at some other point, some amount of time previously, then that's not something that's well defined. Okay? Because someone else could have chosen a different reference frame. Maybe you said this was the origin, but if you change reference frames, then what you're calling x at some value of t in the past might not be what you're calling x today. Okay, so x itself is not a well-defined thing. In general, x and t together fix an event in space-time. But if I just say, what is the field at x equal to 10, or what is the field at x equal to 0? Okay? That's not a meaningful question. And you could say, I pick a particular coordinate system, but then you have to tell me what you did to pick that coordinate system. And if you pick some other coordinate system, someone else would find something different, right? So it's very important that this kind of notation is not covariant. And so, one must have a more covariant way of understanding fields in space-time. So we want to understand, how fields behave in space-time. But in fact, starting from here is pretty easy to understand how fields behave as a function of space-time, because all you have to do is evolve the field forward in time. Okay? And so all you need to do is take this field in our coordinate system, right, and evolve it as a function of with t. Okay? And if you do that, then you will find that these evolution, you see, remember, we already have commutation relations of how h acts, right? So if you convert that into commutation relations for how E acts, okay, you will find that this becomes AP times e to the minus I omega pt plus I p dot x, okay, plus AP dagger e to the I omega pt minus I p dot x. And this quantity that you see in brackets, in fact, is something that's covariant. Okay? And this quantity, in fact, can be written as AP e to the minus I p dot x plus AP dagger where this is now not a 3 vector, but it's a 4 vector, this p dot x, and this p dot x is also a 4 vector. And remember the sign convention that we're using, which is a sign convention where time goes with a positive sign and x goes with a negative sign. Many people use the opposite sign convention, and you're free to use it as well, provided you're consistent. Yeah. Okay, so we'll try and so I could have written psi of x. Let's say I wrote this with a vector sign, and I wrote. Yeah. We'll try and stick to 4 vectors. However, at various times we'll come back to 3 vectors when we need to talk about canonical commutations and so on. But as far as possible, we'll try and stick to some covariant notation, because this is something that actually makes sense. It makes sense to say, at least within the context of special relativity, here we have some event which is x of t, and and there's some other Lorentz frame, and that would be x prime of t prime, right? And whatever properties we have should transform covariantly under these kinds of Lorentz transformations. But at least that's something well defined, as opposed to simply talking about x. Now this is also well defined provided you specify a coordinate system. But of course, what coordinate system I specify might not be the same as the coordinate system you specify. So this kind of representation always has this inherent ambiguity. That doesn't mean there's something wrong with it, but it's not something that can be thought of as universal in any sense. Whereas this is something that's more covariant. Okay. Okay. Is this clear? That we have these fields in space-time and this is how they behave. Okay, great. So okay. Now I want to go back to a question that we started this class with, which was the question of causality. So we've done enough in the discussion of field theory, including the last thing that we wrote, to come back to a discussion of causality. So it's taken us a few lectures, but we've now developed enough of the formalism of field theory to ask this question. Okay. So first, before we ask this question, we have to say a little bit about the nature of observables in field theory. Okay. Now, this is something that's kind of important. In quantum mechanics, all Hermitian operators are observables, right? Okay. So this is, still some postulate of quantum mechanics, but we have to refine this notion a little bit. Okay. And in some sense, maybe this is a little bit of a conceptual change from, the kinds of discussions that you have had in non-relativistic quantum mechanics. Why is this a change? Right? The point is that, let's say we have someone here, right? This is Earth, and this is Mars. And say we have an observer here, and there's a qubit. Okay, there's a qubit here, and maybe there's a qubit here. Right? Now, this is a qubit, okay, and there's a Hermitian observable in the theory that corresponds to it, which is its spin. You can ask, for instance, what is sigma x? Now, can this observer here measure what the spin is? The answer is no, right? Because the observer is in the Earth and the qubit is on Mars. Okay? Now, maybe the observer could wait for some time and wait for signals to emerge from Mars. But at this point of time, if the qubit is far away, the observer can't measure what this observable is. Okay? So it's important that in quantum, and so this, therefore, it can't be the case that we just declare that all Hermitian operators are observables. In quantum mechanics, we just say all Hermitian operators are observables. Right? Now, this is a Hermitian operator, but we don't want to allow this observer to measure this Hermitian operator. So before we start discussing questions of causality, it's important to define a little bit what our notion of observables is. Okay? So observables are tied to space-time points. And this is the new thing that we are going to introduce. And so we can speak of an observable phi of x, where this is a space-time point. And this is something that's meaningful, that's an observable. Okay. And we say, what we want to think of physically is that an observer in X can actually measure this observable phi of X. Okay. Now, there are other Hermitian operators. So, we could also speak of an observer in a region R. So, say we discuss a region R, which can be a space-time region R, right? So, this is our region R. I really need to should draw it in space-time, but I don't know how to draw time, so I'm just drawing it this way. Yeah. And say this is our region R. Then we can speak of which is and this integral runs over the region R, okay, where f is some smearing function. We can associate this as an observable inside the region R. Okay. Similarly, we can think of observables like phi of f1. You can think of products of observables, phi of f2, phi of fn, and of course you can also measure pi. Okay. But if you're allowed to smear both in space and time, then measuring pi is not different from measuring phi. Okay, this is also an observable in R. Okay. On the other hand, if you take integral psi of x, g of x, d4x in the complement of R, okay, so R bar usually stands for the complement of R, which means everything that's outside R. Then, by the way, I should say some. Yeah, I want to refine this a little bit. We will refine it in a second. Okay, you know, this is not an observable in R. Okay. Okay, so this is important. So now, what do we? Is this clear? What I said right now? You know, it might sound a little obvious, but I want you to think about this a little bit because you know, this is in fact is something that's conceptually important when we ask questions of causality. Okay. So what we are saying is that observables are tied to space-time points. You can also tie observables, if you like, to space-time regions rather than space-time points. And the physical interpretation of that is that, you know, you have some rods and clocks, and you have some set of detectors which are spread out across this region R, and they switch on for some amount of time, right? This region R is some space-time region, as I said. And so you have some detectors that are spread out and that kind of, you know, function within this space-time region R. And these detectors can be used to measure the values of this field, this region R. And then, of course, you know, you can think of products of these observables, and this, you know, gives you some more observables that are associated with the region R. On the other hand, you know, there are some observables that are outside R, and those do not correspond to the region R. Okay. Is this clear? Which observables?
So let's say we have some observable in R prime.
In R bar or R prime?
Yeah. So if we can define some correlation between these.
Correlation is not the same as saying that observables can be written in terms of each other. For instance, correlations are a property of the state. Think of this case where you have two. Let's imagine you have two spins, right? And let's put them in an EPR state. In such a state, there's some correlation between SZ1 and SZ2. In fact, the correlation is that these are, once you normalize it correctly, this is equal to -1, because whenever SZ1 is +1, this is -1. Okay, so there's some factor of depending on how you normalize these spins. But you know, this is so you know, SZ2 is correlated with SZ1, but SZ2 is different from SZ1. The fact that two observables their values are correlated in a state doesn't mean that one observable is the same as the other, you know, as the other observable. There are some other states in which these observables have no correlation. So the presence of correlations is different from the question of the independence of observables. And in fact, in the vacuum, it is true that observables in one region are correlated with observables everywhere. So correlations, in fact, don't die off all the way till infinity. But that doesn't mean that those observables are part of R or that we can measure them. The fact that something we are measuring is correlated with something that somebody else is measuring elsewhere is a sign of what's called, actually it's not even necessarily entanglement, but you know, it can be produced by entanglement or by classical correlations. That's not a, you know, that doesn't tell us whether the measurements we're doing are independent or not independent. We now in fact will formulate a criteria for what it means for measurements to be independent. Yeah. Is this clear? Okay, so now, yeah. Yeah.
If we take a particular point,
Yeah.
in that region, so like for that point, like some points will like smear out of the right point.
Why? Why do I have to
It's a
take?
region in space-time.
It's what?
Region.
This is a region in space-time. Yes.
It's supposed to be like inside the light.
Inside the light cone of what?
Yeah, then like take a point.
This is my definition of my region R.
So like the observer itself is like non-local.
There are many observers, so it's not one observer. So I have a detector here, I have another detector there, I have a third detector there, a fourth detector here, and they function for some amount of time. So let's say all of them we synchronize the clocks at one instant of time between all these detectors. So we set up some reference frame, and all these detectors are going to function for 10 seconds, and then their batteries will run out. Okay, they're all over the room. In that case, I can define my space-time region R to be this room from now and up to 10 seconds from now. Okay, so it'll be some sandwich like this, and then this would be my region R. You see, this is 0, this is 10. That's whatever, 10 meters, or 5 meters. Yeah, do you see what I'm saying? So you could think of observe this region R as that. Okay, I want to say something about light cones, but so far I haven't said anything about light cones. Yeah. Okay,
So,
good.
sir,
Yeah.
so this quantity integral over r bar phi of x g of x, this quantity is not an observable in R, but is it an observable in R bar?
Yes, it's an observable in R bar, correct.
So there is an observer who is trying to measure this quantity in R bar region, right?
Well, if there was an observer there, that observer would be able to measure, sure. So,
Okay, so
go on, yeah.
so then I think if I understand correctly, there is some wall which doesn't allow the observer to measure what is in R prime. If some observer
There's
in
no
R,
wall.
he's
Sorry,
not
the
able.
observer, yeah, there's no wall. We just happen to be here. There are other observations that someone in Alpha Centauri can make, right? But we are not there. So the observations we can make are the observations here. It's not like there's a wall between here and where we are, right? There's some other observations somebody who's
Right.
standing somewhere else there can make, but it's then not necessarily any wall. The window's open, but we can't actually make that measurement, right?
Okay, that's why you can't say anything about that measurement.
Well, whether we can say something about that measurement or not is a different question that has to do with correlations, but that is not part of the set of observables in this room.
Okay.
That's some different observable. We have there's some other observables here, right? And the fact that those observables are different doesn't mean there's a wall or anything. It just means that observables are tied to space-time points. So we have to be careful of that when we formulate notions of causality. I mean, the reason I'm saying all of this is because we are soon going to discuss the question of causality. But first we have to ask, what is it that we mean by causality? Yeah?
Yeah, got it.
Okay, good. So, you see, so now we are in a position to formulate a notion of causality and all these questions of independence of observables. Where did I keep this? Yeah. Okay. So let's formulate. I was talking about R and R bar, but say R and R prime are space-like separated regions. Okay. R and R prime are not necessarily complements of each other. They're just two regions which happen to be space-like separated. Okay. So R is here and R prime is somewhere else. Okay. And as we discussed, this is something in space-time. But what do we mean to say that they're space-like separated? What we mean is we draw the light cone from here, and we draw the light cone from here, and this is just outside the light cone. The light cones will always intersect at some point in the future, but no part of R prime is in the future light cone of R. The reason I'm drawing the light cone R like this is because R is a space-time region, okay? But nothing in R prime, no point in R prime is to the future or in the past of R. You understand what it means for regions to be space-like separated? Yes. Then we should have observations in R should be independent of R prime. Of observations in R prime, right? Or should be independent from observations. Okay, what does it mean for observations to be independent? It doesn't mean that, when two observables are independent, it doesn't mean that those observables are uncorrelated in a particular state. Okay? As we discussed, when we say observations on one spin are independent from observations in another spin, it doesn't mean that there's no correlation between those. It could be that we have states in which those observables are correlated. What it really means is, independent is the right word, but let me write, okay, should not be affected, which is actually maybe, okay, should not be affected, should not affect or be affected. Okay. What we really want to say is that observations we make in R do not affect what's happening in R prime, and what happens in R prime doesn't affect what's happening in R. There's a way to formulate this in quantum mechanics, and do you know what that way is? If two observations are independent like this. Exactly, right? So it should be that the observables, that means that if you take O of R is any one of these observables in R, and O of R prime zero, where O is any observable in R, okay. So this is what we really want from causality. Okay, a theory that satisfies causality should have this property, that an observation that you make in R should not affect anything in a region that's space-like separated from R. Okay, and to do this, as we said, we had to first formulate the notion of what observables in R are. So this, when I talk about any observable in R, I mean observables of this kind, right? And OR prime is a similar observable of that kind in R prime. Yeah. Okay, so this is our condition for causality. Okay. Now, you see, is this clear, by the way, what we just said? This doesn't mean that observables in R are uncorrelated with observables in R prime. It just means they don't affect observations in R prime, and you should be clear about the fact that not affecting something doesn't mean that we don't have any correlations. Okay. It could be that we toss two coins, we prepare coins and we put both of them in heads because somebody prepared it that way and then sends them to different locations. If I measure the coin that I have in my box, I might find heads, the other person might also find heads. The fact that those two observations are correlated doesn't mean that my observing here is actually changing what the other person is observing there. Okay, and same for quantum mechanics also in the case of entanglement. Okay, so this discussion I just described was for classical correlations, but even when you have quantum mechanical correlations, nothing that you do here can actually affect what the other person is doing at some other point, which is space-like separated. Okay, so this is in fact the precise notion that we have of causality. In fact, when you studied quantum mechanics, if you studied entanglement and questions of how you have independence of observables, you might already have implicitly used this criteria, and there the way we use it is often by saying, well, if you have observations on one system and observations on the other system, and those two systems are independent, and observables on this system should commute with observations on this system. Okay? But in fact, this is the precise way of saying it. This is what we really mean. Yeah. Okay. And I'm sure you've seen this, maybe if you've seen discussions of why, for instance, you can't transmit superluminal communication using entangled pairs. Okay, and I don't know if maybe some of you have seen it, right? And then you point out that if you move the spin to Mars and one spin to Earth, which is what the picture that we were drawing earlier here, then why an observation here can't affect something there. Okay, but Earth and Mars are really imprecise. That's what we really want to say. I mean, Earth and Mars are not imprecise, but it's just a cartoon. What we really want to say is that, yeah.
We can tell what is happening, but can we change something?
No, it's not even that you can tell what is happening. You see, you can't, you know, if somebody told you the state and somebody told you that you were in the global state, you ask a question. If somebody told you that you were in this entangled state, right, somebody told you ahead of time, somebody already gave you that information, then of course you can, by measuring SZ1, you can know what SZ2 is. But somebody had to give you that information in the first case. That person had to be somewhere here who prepared the state for you. This is your friend. And this friend could give you this information. But then, you know, this friend is actually causally connected both to Earth and to Mars because they sent something here. Okay? So we didn't violate causality here. It's not like the person on Earth independently knows by measuring their spin what the person on Mars got. Because they don't know what the state is. They don't know the state is this or some other state. Maybe it's only this. Maybe SZ1, SZ2 is +1. Till they actually call the person in Mars, they don't actually know what the state is. Now, of course, if a friend here told them the state is this, then this person can tell what's happening there. But then they're using information that came from here. And this person, of course, is in their past light cone, is also in the past light cone of the person there. Then the region R you're talking about is this whole region. And then that is not space-like separated to it. You understand? Okay. Okay, good. So now what do we need to check? To check that the theory we are building is consistent with this notion of causality, right? We started with this story of saying, well, you know, we want our theory to be causal, and you know, we have x and x prime, and if you think of some position operator x, you know, and say that means a particle is at position x and the particle travels outside the light cone and all that story. And so now we want to check that the theory we spent a few lectures building up so far actually does satisfy this constraint. Now you see, the point is that all observables in this theory are basically products of phi. There's nothing else you can do. You can just take phi of x, phi of x1, phi of x2, and you can smear it with different. You can take linear combinations of these kinds of observables. There is no other operator in the theory. This is something we've discussed previously also. If you take a region R and you ask what are the operators in the region R, well, there's phi and there's pi, but since I'm allowing R to be a space-time region, I smear in the right way in space-time, I can always get pi. Is this clear? So this is really the only kinds of observables that you have, these kinds of observables. Therefore, you see, that causality criteria it implies, and it's implied by, in this particular theory, that phi of x this is equal to 0, okay, if x minus y squared is smaller than 0. I emphasize, to avoid confusion, x minus y squared smaller than 0 in our conventions means that x and y are space-like. Yeah. If this is true, if phi of x itself commutes with phi of phi, okay, for whenever x and y are space-like, then clearly any observable that you make in R, which is just a product of phi's, will commute with any observable you make in R prime, because everything here will commute with everything here. Okay. Conversely, this is just a special case of this. When this R is taken to be a delta function, this f is taken to be a delta function in R in this region, and this is taken to be a delta function in this point. So phi of x is in particular an example of an observable in the region near x. And this is an example of one observable in the region near y. And if x and y are space-like, then it should be the case that these two commute. Okay. So you see why this is implied and is implied by this criteria. You see that? So this is the thing we need to check. Okay. This is sometimes called microcausality. Okay. And if you have other fields, all of them have to obey this. Okay. Any operator at point x should commute with operators at point y, where y is space-like to x. Okay. Is this clear? Okay. So now let's check that this is actually the case. Okay, we are in a position to already check whether this criteria is satisfied or not. If it's satisfied, that's great for us. We can go on. If it's not satisfied, it's not so good. We'll have to start from the start. But as you know, we wouldn't have done these lectures if it had not been satisfied. So it will be satisfied. Yeah. Okay. Bad mood again. Okay, good. So we have already have this expression. Oh man, I erased it. Anyway, yeah. So we have this expression for phi. Let me just write it again. Okay, and we want to check this commutator. So let's just compute what this commutator is. Okay. So remember, we have some commutation relations. AP prime dash. This delta cubed is only a delta cube for 3 vectors, and this is also an integral of 3 vectors. Okay, so you want to compute what this commutator is. So we write down another expression for phi of phi, which is exactly of this kind. Okay. And when you compute the commutator, remember it's only the AP from here that doesn't commute with the AP dagger from phi of phi, and vice versa. Okay, it's only the AP dagger from here that doesn't commute with the AP from phi of phi. Is that clear? So you see what will happen when you do that. When you do that, you'll get some answer which will come, well, let me write it. Let me do it in some detail. AK. Okay, this whether we call it P or K is up to us. It's just a dummy index. So let's look at AP.
Is it? Shouldn't that be K dot Y?
Is what?
Shouldn't that be K dot Y?
Thank you. Yeah. Thank you. Yeah. Yeah. Thank you for pointing that out. Yeah. Okay. So let's look at phi of x, phi of phi. Yeah. So first you get some AP and AK dagger. Right. So what you'll get will be AP AK dagger. And then you'll get another term which will be AP dagger AK, right? Is that good? This is kind of, I haven't done anything here. Now we use those commutation relations, which is that AP AK dagger is actually delta cubed of P minus K. Okay. And so that soaks up one integral over K. It just sets K equal to P. Yeah. And similarly, here we have the same kind of integral. So this just becomes e to the minus I P dot x minus y. Do you see that? It's still a 4 vector P. And here, however, we have plus, we have the same thing, but we have minus here, but we have a plus in the exponent. Okay. So we have minus e to the I p dot x minus y. Okay, and this is then just d3p. 1 2 pi also goes away, and it looks like 2 pi cubed, and the square root goes away, and we just have twice of omega p. Okay. Okay, is that clear? So we could write this as, if you like, minus ip dot y minus x, so it's ip dot x minus y. Okay, there's a minus sign here and this opposite sign, the exponent. You see this? Okay, good. So now here's one way to prove that this is okay. So we want to do two things. First, we want to check that this is equal to 0 in the case when, in the thing that's hidden, when x and y are space-like separated. Okay. And then, you know, we also want to check, we also want to evaluate what value it takes when x and y are not space-like separated. Okay. So first, let's check to see that in the case when x and y are space-like separated, this integral actually evaluates to 0. Okay. Okay. You can actually evaluate the integral, and I'll tell you how to evaluate the integral in the case when x and y are time-like. But let me first give you a quick argument why this is 0 in the case when x and y are space-like separated. Okay. Point is first to look at this measure. Okay. You see, this integral doesn't look very Lorentz invariant as it's written. It doesn't look very Lorentz invariant because we have an integral over d3p. However, you know that everything we were doing was Lorentz invariant. So in fact, it should be secretly Lorentz invariant. And the reason it's, you see, in the case of operators there, where I wrote that AP, right, as I emphasized when I wrote the square root of twice omega p, you know, AP was really an operator. And if you chose to normalize it differently, you could just have defined the operator differently. Right? However, now there are no operators left. This is just a number, what we have here. Okay? And therefore, it better be the case that this number, whatever it is something that's Lorentz invariant. That's because everything on the left-hand side is Lorentz invariant. So this number, whatever it is, should really only depend on the Lorentz invariant quantities, which in this case are x minus y squared, the Lorentz invariant distance between x and y. There's nothing else in this problem that's not, you know, that's Lorentz invariant. Okay. Okay. Good. How do we see that? You see, it looks like we have an integral over d3p, which doesn't look very Lorentz invariant. However, you can in fact write that integral. Think of the following integral. Okay. If you think of this integral, which is now an integral over d4p, okay, I'm going to use a slightly, you know, slightly slick argument. If this argument confuses you, you know, we'll evaluate this in a second, and you can check what I'm about to say. However, you know, here's a slightly slick argument. Notice, and this is an argument you should know. Think of this integral, okay, over some function f of p. Okay, this integral is manifestly Lorentz invariant because it has an integral over d4p, which means integral over dp0 and over d3p. This is a delta function of the 4 vector p squared. Now I have inserted a theta of p0. Now that actually, you know, you might have said, well, you're picking out time, but this doesn't break Lorentz invariant because in the case where this delta function clicks, p squared is equal to m squared. So p is a time-like vector. Okay? And you can check that no Lorentz transformation can change the sign of time for a time-like vector. Okay? So, you know, when I'm picking p squared equal to m squared, there are two possible solutions. One of them will have positive sign for p0, the other will have negative sign for p0. I can choose the positive sign for p0 and no Lorentz transformation will change that. Okay? Okay. So this is a Lorentz invariant integral. However, you can do the integral over p0 here. Let's say you do the integral over p0. So you write this as d3p dp0 Now you can do this integral over p0, and remember this integral just looks like integral d3p Vp0 by twice P0. Okay. And then there's another one which is delta of P0 plus omega P, but that's gone because of the theta P0. Okay. And then this delta function just picks up the omega P term. Right? And therefore, this integral, which is a 4 integral, which is Lorentz invariant, is just like doing the 3 integral but setting P0 equal to omega P. Therefore, this integral, in fact, you could have written in this form. You could write phi of x, phi of phi minus HC means minus its Hermitian conjugate. Okay. Let me be consistent with my deltas also. Okay, what I proved here was saying that this expression I have there, I can also write this way. Okay. And now the integral is manifestly Lorentz invariant. Rather than doing an integral, I introduced an additional integral and a delta function. That's sometimes called inserting a 1 in the integral, which is often very convenient. Okay. Do you see? And one more difference is that in this notation, this P here, there's some slight abuse of notation. In this notation, this P was a 4 vector, and this P was said to be omega PP. When we write it this way, this P is really the 4 vector. P is, this 4 vector you're doing the integral, which after doing the integral of a delta function becomes omega PP. Is this clear? Is this manipulation clear, what I just did? Is it clear or are you getting lost?
Sir?
Ah.
Why theta of P0 is Lorentz invariant?
Why? Yeah, theta of P0
P0
by itself is not Lorentz invariant. However, when you combine it with the delta function, you see, when you have, because you have delta of P square minus M squared, that only clicks when P squared is equal to M square, which is some positive number. Okay? So,
Right.
no Lorentz transformation can change the sign of the time of a time-like vector. To say something is in the causal future of another event, or some, a vector is positive time-like, is time-like and it's positive directed, is a Lorentz invariant statement. Right? If I have a vector that points here, I can do various Lorentz transformations which can make the vector point this way or point this way, but I'm never allowed to do something that will reverse the sign of the vector. Yeah? I don't know if you can see this chalk, but this is not allowed.
Yes.
That's why delta of P square minus M square theta of P0 is something that's well defined. And the reason I needed the theta of P0 was precisely to set this sign to be positive here. Okay, because here is a particular sign which is the sign of omega P. I'm not allowed to pick the other sign. If I pick the other sign, this expression would go wrong. That's because this came with a particular sign of omega P, which is a positive number. So I have to pick the positive square root when I do this. Do you see this? And here I'm using the fact that delta of x square is delta of x by twice x, which, and this also, this formula. Where this is the 0 of f of x. And if there are multiple zeros, you have to sum. This formula also you should be familiar with. That's what we used here to convert this to this. Okay. Okay, excellent. Good. So now
in the last line, that P is 4 vector.
this P, yes, this is a 4 vector. Yeah, it was always a 4 vector. However, here we were choosing P to be omega P and the 3 vector P. Here P is just P0 and the 3 and 3 and P, because you're doing an integral over D4P.
Okay, and that P square is 3 vector, right? P square minus M square, that P.
No, it's 4 vector.
Oh, okay.
This is a 4 vector. It's very important this is a 4 vector. When I want a 3 vector, I've written it this way.
Yeah, right.
P squared in this way. Okay, good. Is this all clear? Excellent. Now, say x and y are space-like to each other. Okay? This is the first case we want to do, which is actually what we wanted to check. Okay. Say x and y are space-like to each other. Then notice if x and y are space-like, then there is some Lorentz transformation I can do that will change x minus y to minus x minus y. You see, this is not, I just explained to you that this is not true in the case when x minus y is time-like. There's no Lorentz transformation that can change, x minus y to being minus of x minus y in the case when x and y are time-like separated. However, in the case when x and y are space-like separated, if I have a spatial vector, there is a Lorentz transformation I can do that can take the spatial vector to negative of itself. For instance, just a rotation. I can just go to the frame where x minus y is purely spatial, and I just rotate it. To go from here to being pointing here. Okay. Is this clear that this is the case? If x minus y is time-like, then there is no such thing. Right? If x minus y is time-like, then I can go to a frame where it's purely time-like directed. But there is no rotation that I can do that will change something that's future time-like directed, something that's past time-like directed. However, in the case when x minus y is space-like, then there is a rotation I can do. First, I can go to a frame where x minus y has no time coordinate. And then there's a rotation I can do that will clearly just change x minus y to minus x minus y. Then I can undo the original transformation as well. So such a Lorentz transformation always exists when x minus y is space-like. Yeah. Good. Is this clear? Yeah.
But the determinant of the transformation is minus.
Why?
Because they are changing the vectors by overall sign. So it shouldn't be proper rotation.
It's just a rotation by, if I have a vector which points in one direction, I just do a 180-degree rotation. It's just a 180-degree rotation. I'm not doing something deep. I have a vector here, just turn it around. Why is that a problem? The determinant is not -1. The determinant is +1. It's a rotation of s, it's a rotation in 3 dimensions. Okay. So I have a vector pointed here. I just change it around. It's a perfectly good rotation. Okay, are there any other questions? I mean, just think of an SO2 rotation. Is this clear what I said? Just a 180-degree rotation. It's literally this. This is a vector. This is x minus y. Clearly, right? You can do this. It's exactly that. There's nothing else. It's just a rotation that changes x to minus x. Okay. Any questions?
One more thing. If this P0 is suppose it's a time component of a non-space-like vector, then is that integral Lorentz invariant d4p delta? If the P0 is the time component of a non-space-like vector,
it is
suppose
a
time-like vector.
You mean a non-time-like vector? You mean a space-like vector?
Yeah, right.
No, then it would not be. If I didn't have, if instead of minus m squared I put plus m squared, then this would not be invariant, right? Because of what we just said.
Yes.
So it's important this is minus m squared. It's delta of p square minus m squared. and then I can pick a sign. Okay. Okay, good. But now notice what we have here. We have something as a function of x minus y. We don't know what this integral is. We'll do it in a minute. But for now, we don't know this integral. It's some integral which is a function of x minus y. Just think of this part without the minus summation conjugate as the integral of d4p and so on. It's some Lorentz invariant integral. It's a function of x minus y. And then you have minus of that same integral as a function of minus x minus y. Do you see? So this looks like f of x minus y, whatever f just means this integral. Okay. Okay, where f of x minus y is this integral. I'm just writing it again. Okay, but f of x minus y is just this integral, the first part. This is f of x minus y minus f of minus x minus y. Okay. Clearly, since f is some Lorentz invariant quantity, whatever it is, right? It cannot have different when x minus y is space-like. It cannot have different values for x minus y and minus of x minus y, because it can, if it is Lorentz invariant, then there is a Lorentz. It must be invariant under Lorentz transformations. And there is a Lorentz transformation that can take x minus y to minus of x minus y. So it cannot have different values here and here. Okay. So this is equal to 0. Okay, this is maybe slightly indirect argument, but I hope you can see why it works. Okay. So we've in fact proved something rather important, which is that phi of x, phi of y is equal to 0 when x minus y squared is negative. And that's an important result that we proved. Yeah. And we've already been able to prove it from the formalism that we developed so far. So in fact, as I said, the first thing we started this class with in the first lecture was a discussion of causality. And now we've already proved that the formalism we've set up satisfies causality, in that when you tie observables to space-time points, observables at one point commute with observables in the other point if the 2 points are space-like separated. Okay, good. Let me now evaluate what this is for the case when these are time-like separation. You see, it shouldn't be that phi of x, phi of y is just 0 for all x, y. Right? If that was the case, then we'd be in a position where we have very boring theory, because nothing we do can influence anything else. These are just all independent observations. Right? So it certainly shouldn't be that phi of x and phi of y should just be 0 for all x, y. That doesn't make any sense. So phi of x, phi of y should not be 0 in the case when x and y are time-like separated. And let's see what that is. Okay, I'm going to compute this integral. Surprisingly, in many elementary QFT textbooks, this integral is not actually computed explicitly. I mean, maybe some of you know textbooks where this is done. I'm a little old-fashioned. One old textbook I know where this is done is a textbook by Bogolyubov and Shirkov. They have some funny names for this. They call it Poly Jordan and whatever. I don't know what names they have for it. But if you go open this book, you will find a function, the actual computation of phi of x, phi of phi, and other position space correlators, which later kind of went out of fashion. So you'll find this argument that phi of x, phi of phi is 0 when it's, for instance, in Coleman's notes, in the case when x minus y square is space-like. But you won't find an actual value of what phi of x, phi of phi is when x minus y is time-like. Of course, everyone who works in quantum field theory knows how to do this computation, but somehow it's not written in many textbooks. I'm sure there are other textbooks that also have this. It's not like some secret, but it's just hard to find. Yeah. Okay. Fine. Okay. So I'm just going to tell you how we compute it. Yeah. So what we really need to compute is this integral. Now we don't need a delta function, so we need to compute this thing that we call f of q, right? Check my sign conventions and so on. Sounds good. Yeah. Okay. Okay, good. Yeah. Okay, now the reason I'm doing this integral actually is because it's good for you to know how to do such integrals. Okay, you'll probably find such integrals later. The first thing is that you should, when we have an integral of this kind, you can go to some polar coordinates and you can do the angular integrals. Okay, so you have e to the interesting. I'm trying to see why my signs here are correct. Okay, I think I have some wrong sign in my notes. I'm going to try and correct it in real time. I might or might not succeed. Okay, so you should help me. So we have e to the minus I pq cos theta integral p squared dp d of cos theta for some reason. Okay, rather than trying to do this, let me evaluate this integral. Because otherwise I'll mess up all my eyes and I don't think I'll succeed in fixing this. Minus IP plus IP dot Q. Okay. Sorry, I apologize for that. That's actually because in my notes for some reason I've evaluated this integral. And this is probably what we are calling f of q star. I forget what we defined as f of p. Or maybe this is what we defined as f of p upstairs. Let me check. This is f of p with the minus sign here? Okay, great, fantastic. Then we're all set. Okay, good. Okay, fine, sounds good. So this is f of p anyway. So then it's all good. And I want to evaluate this integral. Okay, this ip dot q you can write as p q cos theta. I'm abusing notation a little bit. I should really like norm of vector p, but this p is not the same as the 4 vector p. Okay, is that clear, or do you want me to write? Otherwise, I'll just mess things up. This is really the norm of p. Okay. And this means the norm of q. Okay. Okay. Same for here. Same this d. Okay. This is not d4p. Now there's one more integral, which is the integral over the azimuthal direction, but that just goes away. Okay? Because that just gives you a factor of 2 pi. That's why this became a 2 pi squared, and this became a pq cos theta. Okay. And remember, what you actually have is a sine theta d theta, but that you can write as d of cos theta. Well, with a minus sign depends on whether you do this from -1 to 1 or 1 to -1. Okay, so we want to do it from -1 to 1, and then it's fine. Okay, good. So this integral you can write as e to the I pq 1 by I. The zeroth component we did. You see, the zeroth component was the integral that we had there. It's already gone. There's no zero component. The integral is over d3p. There was an integral there over d4p, but there was a delta function. Remember, we started with an integral which had only d3p. Then I introduced that delta function to show you its Lorentz invariant. In this expression, I got rid of the delta function and I wrote the integral back as d3p. And I've done the integral of the zeroth component and put this equal to omega p. Is it clear? So I've just put it back equal to omega p. Is this clear, everyone? There's no confusion, right? There we had an integral of d4p, but there's also a delta function. So I've not written that, but I've done that integral. That's why this became omega p. Okay. Now I'm just looking at this integral, which is, I'll put this back in. I'll put it back in. I just want to look at this integral. Okay. So this integral looks like okay, and then we have an integral over. Sorry, maybe I should write it. Maybe let me write it. Okay. So what happened here? What happened here is that we did the integral over e to the I pq cos theta. We did the integral of cos theta. From here we got e to the I pq minus e to the minus I pq. Okay, because we did from -1 to 1. Okay, and then we pulled out some 1 by iq. That's just in doing the integral. And one of the p's got cancelled, so we had a pd. Okay, and you have a 2 pi square twice omega p. Okay. This is kind of useful that this p gets cancelled, because what we have now is something that's odd in p in the bracket, and we have something that's odd in p in the bracket here, and all this is even in p, the omega p. Okay. So this integral over p actually goes from 0 to infinity, because remember it's a polar integral. Okay. So you can write this in fact as 1 by iq integral minus infinity to infinity q0 I pq p dp by 2 pi squared twice omega p. Okay. Okay. And such integrals you can then, this is now, okay, so is that clear, that part? This you can write as -1 by 4 pi q into d by dq integral minus infinity to infinity q0 e to the I pq, okay, by 2 pi squared omega p. Okay. Okay. So what I did here is I just wrote a d by dq. So I had something here which looks like a p here. Now this p I can just think of as differentiating with respect to q. If I differentiate with q, I pull down some factor of ip, and I hope I got my signs right. Yeah. So I wrote this as 1 by 4 pi q, and then you see 1 by I can write as minus I, so I think my signs are correct. And this should be minus. Okay. If my signs are not correct, please go back and check, but I think they are okay. And Excellent. Okay. Now this is just some integral which you have to actually go look up, and the way you have to look this integral up is the following. You make the following substitutions. Okay, now it's annoyed with me, but oh, you want to try it? Last time Ashik was very good. He would just touch it, it would go. Let's see if you have the same this thing. You don't have the same golden touch, man. It's okay, it's fine. Don't know. You can try, but it's okay. Anyway, we are reaching near the end. So, yeah, Ashik would just come and he would just like press it and it would just go up. But well, maybe one of you has it. You can try. Okay, good. So we want to make some substitutions here, and the point is to write omega p as m cos phi and p as m sin phi. The reason this is useful is because then omega p automatically solves the equation that omega p squared is m squared plus p squared. Okay, and if you do that, then dp becomes m cos phi d phi. Okay, and then dp by omega p just becomes 1. Sorry, just becomes d phi. Yeah. Because we have dp by omega p just becomes d phi. Okay. So this integral after substitution, similarly we can write this guy q0 as write it as rho times cos phi naught. Where rho is just the space, rho is just the norm. You can write q as rho times sin phi naught. Why am I allowed to do this? Because I only want to evaluate this integral in the case when q0 is when q0 squared is larger than q squared. Okay. Therefore, I'm allowed to write q0 as rho cos of phi naught. Okay. If you evaluate, let's evaluate it first for the case where q0 is positive, and q as rho sinh of phi naught. Okay. Because in this case, q0 squared is larger than q squared, and rho here is just square root of q0 square minus q square. Okay, rho here is norm of, maybe my rho looks like a p. It is alpha. Okay, so alpha here is just square root of q0 square minus q squared. Okay. Is this clear? I'm just making some substitutions. I'm not doing anything deep. If you do this, then you will find, if I had all my things correct, that this looks like minus this one. This is just a change of variables. The motivation is what I'm about to write right now, but I'm allowed to do this, right? This is just changing from q0 q to alpha phi naught. So there's no integral over q also. So let's just do it. I'll tell you what the motivation is for very simple. It's the fact that this is going to become, you see, this looks like m cos of phi times alpha cos of phi naught. Okay, and then you get here sinh phi and sinh of phi naught. So that just starts looking like cos of phi minus phi naught. So this will look like e to the I minus I. So this looks like, let me write, minus 1 by 4 pi q, okay, d by dq, integral e to the minus I m alpha cos of phi minus phi naught. That's why we did it, to write this as cos of phi minus phi naught. Okay, okay. Now this integral is something that can be done, and this integral has some value. I'll tell you what the value of this integral is. Okay. By the way, what I'm doing right now is not super important. In the end, there's going to be some answer, but it's not super important. I'm just trying to tell you how, just trying to give you a sense of how these integrals happen. Okay, yes. Now I ran out of space in this board. Okay. Okay. Let me try and squeeze. Okay, I'm sorry, I can't put the board up. I don't want to erase also, so I'll try and squeeze what I can do. Yeah. So it turns out that this integral e to the okay, I'm going to go back and check these signs because I have some mismatch in the signs between. I'll write down some answers, and when we come back at 4, I'm going to tell you if my I signs are correct. Okay. Huh? Oh yeah, here, right? Exactly. Yeah, it's certainly. Okay, I'm going to write down some answer and then I'll come and I'll tell you guys later if my signs were all right. What I have in my notes is that e to the minus I omega pq0 pq dp by 2 pi into omega p is equal to I minus I by 2 sin q0 is j0 m alpha minus n0 m alpha. Okay, my alpha is square root of q0 square minus q squared, and m is of course omega p square plus p square. I'm a little uncertain about this sign. Okay, so I'll check whether this is minus I or plus I, but I'll tell you at 4 o'clock. Okay, and in the case when x minus y is time-like, so once we have this integral, we are done, right? Because this integral is just, you just evaluate it from here. And once you have this integral, you just have to differentiate it with respect to q0, with respect to q, to get the answer. Okay? And when you do that, the answer is again up to a factor of I, which I'll check. Where this J0 just becomes a J1 because once you differentiate with respect to Q, you get a J1. Okay. The other part just cancels because remember, you have to take this and you have to subtract off something that's its Hermitian conjugate. Okay. When you subtract off its Hermitian conjugate, the sign of Q0 changes. So this part doubles, but that part just gives you 0. Okay. And the whole answer is proportional to an I, and you shouldn't be surprised by the fact that it's proportional to an I, because the commutator is something that's anti-Hermitian. So its expectation value should always be proportional to I, and in this case it just happens to be a number, and if it's a number it has to be a purely imaginary number. Okay, and this J0 turn into a J1 after you differentiate. Yeah. So this is the value of the commutator for the case when when x minus y square is greater than 0. Okay. So in the case when x and y are time like separated, you get some commutator. It's this, the fact that it's J1 is not important. That's why you don't find it in most textbooks. But you know, it is J1 in this case of a massive scalar field in 4 dimensions, and it's 0 when x and y are space like separated. Okay. This is really the important fact, the fact that it's 0 when x and y are space like separated. And this tells you, you know, that this commutator, you know, is vanishes when 2 points are space like separated, and that's what makes this quantum field here in this formalism that we're doing consistent with causality. Okay. But when you're in the future light cone, then you get some expression which tells you how one observation here affects the other observation. Okay, good. So we can stop here. Are there any questions? Huh? Well, from this integral, you just have to go look up in some Russian book, okay, and then you'll find that it's this. Okay, this is actually, you know, one of these McDonald functions. It gives you a k0. You know, it's n0 plus I j0. So that integral you just have to go look up this integral. Okay, and that's where you get this from. Then you have to just differentiate it, do a d by dq. How do you get this integral? This is, you know, it's some integral which some special function. And there's probably some better way of showing that it's k0, but it doesn't matter. You know, this is some known integral. This kind of special. You go look up these books; they'll have integrals of this kind. You know, what I wanted to give you in this manipulation was actually not this. What I wanted to tell you in this manipulation was first how you do these angular integrals, which is something that's useful to know. How in the case of 4 dimensions, by the way, this doesn't happen in other dimensions, these angular integrals that you have from 0 to infinity become integrals from minus infinity to infinity. And how in these setups, it's often useful to go to these light cone coordinates and make those kinds of substitutions like the ones we have in the top box. Okay. The fact that you do these substitutions and you get J1 here as opposed to, I don't know, J2 is not very important. But you should kind of know these techniques. I mean, when you write a paper, it'll be important that you get the right answer. Okay, but for this, for what we are doing in this course, it's not very important for this precise values. Yeah. Okay, good. So let's stop here and let's meet again at 4. By the way, 4 is okay, right? Is it very problematic? I hope it's not very problematic. That was the time you guys settled for the tutorial anyway, right? So I'm just taking the tutorial. Yeah, that's fine. But this is a regular thing that you have. That's something you should discuss with Manish. Okay, fine. Yeah, so but 4 is the tutorial time, so I'm just taking the tutorial time. Okay, sounds good. So let's meet then.